Very sorry I haven't brought any Lego with me. I'm more on the theoretical side. But what I'm presenting to you today is some results from experiments we did actually. So privacy over machine learning data-driven economy. It's worked together. I did together with Bernd Malle, who is a colleague of mine. Couldn't be here unfortunately. So he's the machine learner actually. I'm the security guy, and so we work together. SBA is a research center for IT security situated in Vienna, and if you're interested, of course, in collaborating, we're very open to everybody, so we're also very open with collaborating with some companies as well. But more interesting thing is what I'm talking about. I'm talking about huge amounts of data, as you can see on the slide, where I was remembering these things. And what are we talking about? Well, data is becoming a resource, and we're talking about data-driven economy. We're talking about putting machine learning algorithms to use, on working on large collection of data, singling out interesting individuals, singling out interesting facts. Actually, also in the realm of IT, having millions of sensors collecting data, making sense of the data. And this is quite interesting from a security perspective. Let's say there are some things that are interesting. Of course, standard issues like data protection, regulations, especially now with the new data protection regulation from the European Commission and all these kind of things. Manipulation detection, of course, data's got a value, and data, when I want to make sense out of my data, somebody could try to make me feel safe, make me make wrong assumptions out of my data collections. Privacy protection, something that's gotten into the focus during the last recent times more and more. We're even more now with the data protection regulation and such things, it's really getting into a legal status. Before it was easy, everybody talked about data, about privacy protection, but nobody really cared. Now, you know, there are penalties and such things. All the trades, of course. If I calculate something based on my data and I make assumptions out of it, I sometimes have to prove the data I worked with wasn't manipulated with. Forensics, resource protections, and one thing that's quite frequently forgotten, that's actually the main topic of my talk today, that's actually all the effects of privacy on machine learning. So everybody's talking about machine learning on large data sets, and everybody's talking about protecting privacy. But what happens if I protect privacy and then run machine learning algorithms on my data, on my protected data? So let's have a look at privacy in 21st century. So let's imagine technological progress is a huge cup of boiling coffee. And privacy is the sugar in the coffee. So that's the thing we want. The one thing we have to make sure is that our data protection laws somehow really still work. It's not like a spoon feeding the sugar to the huge cup of coffee, it dissolves and doesn't make sense anymore. So this is something really have to keep track on, that the privacy, let's say privacy in the age of data-driven economy has two main issues. The one is I have a lot of usability, which could be potentially hindered privacy, or reduce usability. On the other hand, it could happen that my privacy simply dissolves in all the huge data sets that are collected. There are actually two more precise things that typically are talked about nowadays. The one is the right to be forgotten, and the other one is anonymization. And while they seem quite the same thing on the first glance, they're actually very different. And that's actually something we want to talk about. We did actually, so the right to be forgotten is simply you have the right of the user to have data being deleted. You have a data set, this data set contains user data, and somebody, you're now obliged to delete this data if somebody requests it. In the past, deletion was something like, okay, your data won't show up in search indexes, or let's say I somehow don't tell anybody anymore that I have your data or something like that. But there are now changes also in regulations, which are now really focusing on actually what does deletion mean. Deletion is not a really simple, it's a really complicated question. If I want to delete data, what does it mean? Well, let's assume a database. I have data in my database. Now if I say delete from table, is this deletion? I mean, it's not even overwritten, it's just unlinked from the search index. I have trails of the data in all my audit logs, in my audit trails, in my backup, even in the database itself. And of course, if I'm doing machine learning, I have the data also in the databases, in the knowledge bases I use for my machine learning algorithms, where I train my machine learning algorithms on. Do I have to relearn my machine learning algorithms? So, if we talk about the impact on different database layers, for example, that's why I actually say that I have system internal data stores, I have statistics I calculated out of the data, which I should need to redo in the end, and of course I have the machine learning performance. So let's talk about machine learning with performance bit, because this is something, a decisive factor. This is something that will lead to a lot of discussion regarding data protection in the first place. Because if data protection is not, let's say, assume we are in a country with strong data protection laws, and all our companies have to oblige these laws, then there is the danger that we somehow will lose to countries with less data protection laws. It's like environmental laws. Some things are produced in different countries because they don't have these kind of regulations. So we need to understand what it really means if I have the right to be forgotten, if I have to oblige some, if I have to obey anonymization laws. And we did 2 experiments actually. We call it two different things. The first one is exercising a user that actually executes the right to be forgotten. So we have we have machine learning algorithms, and we now have a knowledge base where we train our algorithm on, where we then get results, and we then have users really removing the data from our knowledge base. The second one is not having the right to be forgotten, but on the other hand, seeing the effects of anonymization on our machine learning algorithms. So this seems, let's start with the first experiment. Security deleting valuable data points, and I will talk a lot about experiment setup because this is very, very important. We have some results based on these experiments, and it's very, very important to have these results put into the whole context of our experiment, what we actually really did. So, selectively deleting valuable data points. What are valuable data points? You can ask. I mean, let's have a look at the data set. It's not about what's written here, it's just for you to get a feel. It's actually census data from American US census data. It's, I think, about 25 different parameters in reality from the US Census showing persons. In our experiment, or let's say the base experiment is, we have this data set, and we train a logistics classifier on it. This classifier shall tell us, based on some parameters, if this person owns more than $50K, I think it's $50K, but above a certain threshold in money or not. And of course, if we use this data to train, there are some parameters that are more valuable than others. For example, my monthly income, gross income, may have something to do with the money, with the amount of money I own, sometimes at least. On the other hand, I don't know what you ask. The height of my body is maybe not, or my body mass index, or even the location I'm actually living might not be so important. Location is, let's say, in the middle. So what we did is we actually analyzed this census data and found out, trained an algorithm to find out which are the most important parameters. And those are the parameters we're now removing. So what we did is now selective deletion. We extracted the 3 most valuable attributes because we wanted to have a worst case scenario, of course, and which contributed the most information to classifier, and constructed new data sets. We assumed that 20%, 40%, 60, 80, and even 100% of the data owners actually deleted their information from these parameters in the data set. So in the best case scenario, 20% of the people wanted their most valuable data clones to be deleted. That's the experimental setup. we actually used 4 different classifiers on it and calculated the F1 score. The F1 score is a measure for accuracy of algorithm. It's more or less a harmonic median of precision and recall. It's quite standard. There's always this discussion is if the F1 score is really the thing to judge the algorithm by. There can be a lot of discussion details. We chose it, we selected mainly because we originally did this work for medical data. And in medical data, they actually quite often use this kind of score, so it makes sense actually in comparing it here. And this is quite an interesting result actually. So we had 4 algorithms. So here we show 4 algorithms: gradient boosting, a spot vector machine, logistic regression, and random forest. And I don't want to actually really talk about the values, but what's interesting is the form of the curves. So you see, I mean, in the best case, we actually have 20% of people, 20% actually really making use of the right to be forgotten, which is quite a lot actually. Saying that I don't want my data, your most valuable classifiers, to be used for training algorithms. And the impact is actually not really, we expected far more impact on this. Actually, we started with 1% and 2% of persons and simply didn't see any effect. That's why we did the experiments with so many users. Of course, if you really remove the most valuable data sets, after a while, it starts to go down, it starts to dwindle. But still, it's actually quite interesting that the right to be forgotten hasn't that much impact than we originally expected. So, this was the first experiment. Second experiment was of anonymization. So, instead of removing valuable information from dataset for certain individuals, we flatten, we reduce the quality for all of them, more or less. What we did, we actually used k-anonymity. Why we used academia was k-anonymity because it's quite, let's say, it's more the general case that's typically used in academia, also in the medical sciences. They're quite really fond of k-anonymity. So the idea is having slight changes to all records, whereas hefty changes to certain records. And for the set, I want to have some standard notation. When we look at especially medical data, we have actually 3 classes of columns. The one is identifiers. Identifiers are simply columns that identify a person. It's your name, for example, your social security number. It's something which I cannot really, where I say, okay, I don't anonymize it, I just throw it away. Second one, sensitive data. That's typically a payload I want to analyze. So we usually keep it. It's like you have lung cancer in whatever stadium and whatever. And the third is quasi-identifiers. These are actually data particles that in themselves are rather unproblematic, but in combination can help to actually identify a person. This was quite a very nice work from 2002 actually from Sweeney, where they actually proved that, don't beat me, I think it was 74% or 75% of all American individuals can be identified by using the tuple birth date, social birth date, gender, and Postleitzahl. Quite simple. We take all the columns that can be problematic for identification, like those identifiers, and change them in a way that at least k of them, k is a security factor, the security margin, are the same. So that one, you cannot, if you pick out one of the records, it's unidentifiable from at least k minus one other records. That's quite a standard technology, and it's the basis for tons of other anonymization techniques and anonymization paradigms. So this is just an example. Here you have 3 records that you cannot change. Typically, you typically have a trade-off, of course, and that's data utility. So if you, here I lose, if I do this, I lose information. I mean, it's quite obvious. Here, for example, I had, for example, all the zip codes, and you just reduce the information gain I have. So I always have this problem. I have only one thing, data utility versus privacy. I can switch how much I want from one of them, can't have both. Yes. For our experiments, we actually use generalization. So there are many ways of achieving k-anonymity, as you might see. We more or less use generalization with a bit suppression, but good generalization. What does generalization mean? Well, it means if I have very granular data, I reduce the granularity of the information. So instead of saying, for example, I have men and women, I just say I have persons in order to achieve k-anonymity. If I say I have, for example, people born, I have the birth date down to the day, I just reduce the granularity for everything, for every data record to the month, to the year, something like this. So it's a very, very common technique. Yes, what we did, some side parameters that's made quite important. We used a very simple form of generalization, a very general form of generalization to make our results more general. You know what I mean, okay? And also for the suppression, we only used, suppression means deletion of data objects. We scarcely made use of that. Why I'm going in so much detail of this is because for the results it's quite important if you later study the results, what we actually did. Anonymization is a very, very broad field, and there are tons of different paradigms on how to motivate anonymization actually to say what motivation is actually. So what we did, we actually used a very common but quite new algorithm, the Sangria algorithm. I think the acronym was before name, like always. And why we use this algorithm was actually because it's a very general algorithm. It not only works on tabular data, but it also works on graphs, for example, social graphs and such kind of things. And it's a Sangria algorithm. What it does, it looks like what it does is, if k-anonymity is not met, it tries to combine data points, either rows or points in a graph, in order to achieve k-anonymity, to get better, to get more close to k-anonymity. And it goes on, adding and mixing up points, combining points until k-anonymity is achieved. You can, if you have the picture inside, it's just like you have a cloud of points, and you combine as you try to combine them into classes until you have classes that all have at least k and the elements. So it's kind of greedy approach. What you need, of course, is some kind of metric to see what information you're losing. And here we use actually generalization information loss metric. The idea is actually, if I add 2 points together, 2 data points together, I somehow define what's my loss in granularity, what's my loss in value, in utility. It's typically done with this nice formula, which is very interesting for calculating, but it's actually quite simple for examples. For example, if I have an overall range, for example, for age, going from 11 to 91, and I cluster the nodes in intervals of 10, then I have, which means 8 intervals in the area range from 11 to 91, then I have a cost or an information loss of 1/8. If I generalize a hierarchy which has 4 objects, for example, into one, Austria, France, Portugal, and what was to Western Europe, I forgot one of them. If I have 4 of them to Western Europe, then I actually have a generalization cost of 1/4. So it's actually quite simple for the data case. What I also have to do is, of course, I have to decide when when a point can be added to 2 different anonymization classes, which choose. For example, this one, this data particle could be added to both classes. Either I generalize on for example, the state going to North America or going to America, or here I still have, for example, the legal status, here I don't have the legal status. So this is simply a question of when to, or of what to choose to over the other. You can do this with weight vectors, and this is actually quite simple. So now for the experiment. Why I added all this kind of stuff is because it's important to see for the summary in the end. What we did now is we used several k factors. So we said, okay, we want k anonymity of 3, k anonymity of 7, 11, 15, 19. And we also had, we also wanted to study how the weight vectors actually work. So once we preferred age, and another time we preferred race in order, if we had a data point where it's not which we could add to two different classes. So this means 15 different randomized data sets. And what's the interesting part, now we come to the interesting part, is actually the huge effect anonymization had on our results. So when you can remember the curves from the right to be forgotten, which were actually where there was not much actually loss in accuracy if I removed like 20% of my most valuable columns. But here and now, I have a k-anonymity factor of 3, and I lose really a huge amount, or I have a really steep drop in the data utility, which was also surprising in the end. So I have to take the time. So, what were our conclusions from our experiments? In our experiments, the right to be forgotten seems to be surprisingly unproblematic for machine learning algorithms. So with the setup we used, we actually didn't get that much impact compared to anonymization. And a k of 3 in k-anonymity is a very, very low factor. So if we talk about medical environments, you often use really much higher factors for this k, for anonymization.
Sorry, how big was the data set?
Over 3,000.
Okay.
3,500, I think, data sets. It was a subset of American US Census data.
And how many features?
Totally, I think 24, 25.
Okay.
Yes, but we removed, for example, right before we removed the top 3 only. We didn't remove everything because then you've got an empty table, which doesn't make sense to make machine learning on. In the end, for the right to be forgotten. The other thing that we really find out is that, for example, we really have to investigate in the algorithms that really can deal with anonymized data. And even if we say we cannot deal with anonymized data, at least having some boundaries, some thresholds, or getting some idea how my algorithm works on the anonymized data. The problem that's also of course prevalent is that I'm always capable of constructing data sets where my specific anonymization or deletion technique is extremely problematic. And that's especially a problem if we're talking about finding rare diseases in medical data sets, where only a few people actually have this condition. Here, for example, the right to be forgotten can be extremely problematic. But still, the surprising thing was if I take, let's say, a realistic data set, remove information, I still can say something about it. Yes, future work is, of course, extending this to other perturbation techniques. Adding noise, for example, which is very typical for anonymization, which we didn't actually currently see. Having more advanced aggregation rules, for example, microclustering resources, especially in graph-based data sets. And especially for graph-based data sets, we actually also want to have a look at graph perturbation. Graph perturbation actually works if I've got a network graph, I just randomly remove and add edges and nodes and so on, and add new ones. So this is actually something very interesting because it's very cheap, and it's very, very hard to calculate back. So this was, of course, just an excerpt. There's a full paper with more details also on the exact number of data points and so on, which is, of course, which you can, of course, get on the internet. It was published in the IRIS conference this year, and you can also contact us, of course. Yeah. You'll find our address. And well, yeah. If you have questions, you can also ask me now. I think we still have 1.5 minutes left.
Okay, thanks to the speaker. Are there questions?
Maybe it would make sense to have opportunistic algorithms which go for the entropy in the actual content of the data feed and try to preserve that.
This is a good thing. I had no slides, something that we are currently, I mean, the problem is we are typically not allowed to select who is deleting the data. But what we're currently looking is having anonymization techniques that actually preserve the statistical attributes of a data set, so that you might not, even if you remove a data particle, that you can still preserve attributes, or at least have a guess or have an estimator how it changes. There are two problems actually. The first problem is a simple big data problem. We have a data-driven economy, especially if we're talking about a lot of data, that I have to know a lot of things about my data information. I have to have a complete model about my data in order to be actually capable of doing this. If we're talking about the big data approach, where I simply say I throw machine learning at large amounts of data I don't know much about in order to find correlations, then we have a problem in this respect. But yes, this is something we will have a look at in the future, or we want to have a look at in the future. So this is quite work in progress for us. We started with this some months ago, and now have the first paper out, and try to have more interesting results, also more results in the upcoming year, which is our, yeah. It's also regarding the legal perspectives, it's still very questionable of how much impact all these rights that we've got now have to shorten will really have. So from a legal perspective, what you really will want from us.
If I were to say that I remove some points of data, and especially now given the rise of something that takes us longer to train, like neural networks or other more complicated machine learning algorithms, what do you think are the problems that arise given that each time you delete the point of data, you have to retrain all your models? So where do you see problems there with the training time and so forth?
I see. I think you singled out the problem here. I think this is a huge problem.
Yeah. But what would you do? How would you go to not solve it, but maybe get some solutions against it?
In my opinion, currently it would be interesting to actually have estimators on what's the actual impact. If we can calculate, estimate, and say, well, we're still good in the boundary of, let's say, a certain threshold factor, then maybe we don't need to recalculate every deletion, point of deletion, but every, I don't know, after a while. The next could also be a regulatory solution, which is the cheap way out, but saying things like, okay, I have a certain amount of time till I have to obey this right to be forgotten. Let's say I don't have to delete immediately. I mean, which doesn't make sense in technical sense anyway. So we still always have to have some kind of, let's say, threshold on the time value. So maybe we can say, well, let's redo it later. There's always still the discussion: can I obfuscate the data? Can I still use the trained algorithm and just remove it from my knowledge base, so that just, let's say, have the effects taking place at the point of retraining? But this is something which is a legal aspect. Currently, we are of the opinion that we have to learn more about this problem, first in order to actually give guidelines for the legal questions, and also to be prepared, because when the legal requirements are here, it will be quite late of then starting to think about what are the effects on my whole system.
Okay, then thanks again to the speaker, and
Thank you
we now have again a short break.
Thank you for